is then a good approximation. In fact, the harmonic oscillator neglects two essential properties. The first property, as I said in the very beginning, that when the distance between the two atoms of the diatomic molecule increases, well, the harmonic oscillator says, as it shows mathematically, that this distance can increase indefinitely with no limits, which is not true, right? Because if I increase the distance, well, at some point the molecule, the two atoms, will just break together and the molecule will dissociate. And it neglects that when these two atoms get close together, the distance between them is smaller than the equilibrium distance, well, they will start feel repulsion. So at very small distance, they will start repelling each other. So these two phenomena are neglected in the harmonic oscillator. So basically, a vibrating molecule, diatomic molecule, is not really an harmonic oscillator. So what is that? It is basically a non-harmonic oscillator, or a so-called anharmonic oscillator. Anharmonic oscillator. Well, as you will see in an anharmonic oscillator, there will be the selection rules of delta nu equal 1, delta V, equal 1, but there will be also 2 and 3, which means that, say that a molecule is vibrating at the energy corresponding to V equals 0, so the ground energy of vibration. Well, it can absorb light to go to the vibrational level of energy just above it, corresponding to V plus 1, but it can also go to V plus 2 or also to V plus 3, but with much lower probability. But this explains, in fact, the harmonics that we have seen in the experimental slide just at the very beginning. Now, I don't need to go into the details of the expression of the Morse potential. You can read it if you want. I don't want to get into that. What interests me is this. What happens is, as I said, the Morse potential, I'm being redundant now if I explain again what happens, but you see clearly the difference with the harmonic approximation. When the distance gets increased between the two atoms, well, there will be a level of energy after which the molecule will dissociate. And this will allow us to calculate the dissociation energy. Okay? Well, as you see, there is something called D0 and DE. We'll see in a moment what it is. Now, how does that differ from the harmonic oscillator approximation? Well, as you will see, if we put this Morse potential expression that you are not responsible for into the Schrödinger equation, then we will get into solution for E, which will show us that as the energy of vibration increases, or as the number V increases, the spacing between consecutive energy levels of vibration gets smaller. And in this way, we will be able to see different lines on the spectrum, and they will not all overlap or coincide on one singular line on the spectrum, as it was the case for harmonic oscillator. Let's see if this gets a bit more clear. Well, I don't care about that. I care about this. Now, putting the expression of Morse potential into Schrödinger equation, doing the crazy math, we get into this. This is the expression of the energies, the energy level of the molecule, when we consider that it has an anharmonic oscillator. So it's h nu e v plus half minus h nu e x e v plus half square. Okay, nu e is the frequency of the oscillator in the simple harmonic approximation. So that's what we've seen before. That's the 1 over 2 pi radical k over mu. Okay, so that's nu e. Xe is a constant that has no dimension, which is much smaller than 1. Now, the nicer spectroscopic way of expressing it is like this. Again, we go into the spectral vibrational term GV, which is nothing else than in units of wave number. So it's the energy divided by hc. We do that, we get into, so if you divide this by hc, you will get nu e over c, and here you will get nu e over c xe. And this is nothing else than omega e that we've seen before, and omega e xe. So this is what you are responsible for. That's what we are going to deal with in the spectroscopy. Okay? Now when I said responsible for, it somehow means you need to know it. And usually we don't give that in the exams. Usually we don't give that, okay? So yeah, you need to know that. You need to know that omega e, which is basically nu over c, with the nu being 1 over 2 pi radical k over mu, this is just classical mechanics. But then you need to remember that basically, yes, well, this is harmonic oscillator, and this is a correction due to the anharmonicity of the oscillator. Okay? So it's called anharmonicity correction. Voila. Okay? Well, you can see here as V increases, because there is a square here and there is a minus, well, then the energy is going to be higher, but the difference between consecutive levels will get smaller. We will see that. Look at this. The selection rules are slightly different, as I said. So obviously delta V equal plus minus 1 has the highest probability. So usually the molecule will absorb light, usually to go from one level to the one just next to it, higher in absorption, and same thing in emission. But there is a possibility, which is not zero, and it exists, and it gives the lines that corresponds to the harmonics. And notice, harmonics here has nothing to do with the harmonic oscillator and anharmonic oscillator. These harmonics are just the lines that are multiples of the fundamental line, right? So these harmonics that will show up on any spectra or spectrum will basically come from transition that could happen from an energy level. In this case, it's an example that it's the 0, but that goes to other ones. Now, notice that as we talk about harmonics, we talk about fundamental. The fundamental line, or the fundamental spectral line, is the one that has the highest probability. Now, as it's fundamental, it's usually when we go from the lowest energy level, so the corresponding to V equals 0, and we absorb light to go to the one just after it. So it's we go from V0 to V equal 1. So the delta, spectroscopically speaking, or delta E, or basically if we divide by HC, we get into new spectra, new bar spectra, which is delta G. It's GV minus GV0 with V equal 1. Okay? This gives us the fundamental. So when I say that I have fundamental line and harmonics, this happens when the first or the initial energy from which the molecule moved to higher energies is the one equal to 0, right? So the fundamental one is nu bar 1. Just do the calculation. You have GV and you have GV equals 0. You have that. It's just here. Okay. You just make V and V equals 0. You make the difference between them. Put V equals 0, and then you keep the other one V. You do the small math, and you get into this expression. Now, if it goes from 0 to 1, then the final state corresponds to V equal 1. Then you put V equal 1, and you get omega E minus 2 omega E xe. The first harmonic will be from 0 to V equal 2. So the final state corresponds to V equal 2. You just put V equal 2 here, and you get 2 omega E 6 omega E xe, and the same for 3, etc. And obviously, the probability gets lower and lower. So the more we move in harmonics, the more the peaks that will show up on the spectrum will be low and low and low in intensity. Now, this is something that we will see in the exercises, and I can tell you this is something that more than one time showed up in the exams. Okay, so look at this closely. It's not difficult. Now, one other thing, as we did in the rotation, you remember we explained it at that time, and it was a bit tricky, so some of you asked me questions privately, and I explained them, and I will be happy to do that also afterwards. But look, there will be different transitions, different peaks on a spectrum. Okay, so I will talk about the transitions corresponding to delta V equal 1, which means I will not talk now in this next slide in 44. I will not be talking about the harmonics. I'm just talking about the fundamentals, but going from 0 to 1 or from 1 to 2, from 2 to 3. So delta V equal plus or minus 1. In absorption, it's going to be plus 1. Then, if I am to see that this line, which will show up at nu bar spectrum, so this is the wave number of the spectrum, on the spectrum, well, this comes from what? This comes from a transition from one level to the other, so that it's a delta V, where V goes from V to V plus 1 in absorption. So it's the final spectral term minus the initial spectral term. So if you put V plus 1 in here, and then V as this one, and you make the difference between them, you will get to this nice expression. So the delta between two energy levels will give us one line on the spectrum, and this is going to be at the wave number omega e minus 2 V plus 1 omega e x e. Okay, V here is the one, is the initial. So if I tell you I'm going from level 1 to 2, okay, calculate lambda or nu bar spectrum, and you are to use V here. If I'm going from 1 to 2, then V equal 1, not 2. Okay, so this is important to remember. What is more important is that if I give you an experimental spectrum and there are different peaks showing up of absorption, and if they have high intensity, so clearly these are not harmonics, these corresponds to different transitions, each one of them is obeying delta V equal plus 1, then the difference between them is the difference between two nu bar spectrum, between this nu bar spectrum and this nu bar spectrum, or this nu bar spectrum and this nu bar spectrum. If you do the difference between them, whatever V is, you just take nu bar V plus 1, so you put instead of V here V plus 1, and then you use the V and you make the difference between them, you will find, just small calculations, very easy calculations, that the difference between two consecutive peaks on the absorption spectra of vibration is nothing else as 2 omega e x e. Okay? So from this you can get 2 omega e x e experimentally. And then if you are to study this, then you can actually also know what omega e is if you have the fundamental. Okay? So this is how the exercises go around. Okay? Remember, in rotation, this difference, I think, was equal to 2b. If you have understood that 2b, then, while in vibration, same. But the difference between two peaks, big ones, not with harmonics, it's 2 omega e x e. Now, when it comes to harmonics, so now I'm not talking about delta V equal plus minus 1, it's plus minus 2 or plus minus 3, etc. As I said before, we have seen that earlier, it's between V equals 0 going to any other V. So the spectral line here is corresponding to a transition either from V equals 0 to V equal 1, okay, or from V equals 0 to V equal 2. So if I put 1 here, you will see that it's going to be equal to omega e minus 2 omega e x e. So that's nu bar 1. If you put V equal 2, so it's going from 0 to 2, then you have 2 omega e minus 2 omega e minus 4 omega e, so it's 2 omega e minus 6 omega e x e, and this is exactly this set of things. It's just written, it's just written it again here. Okay, so not really difficult, just to know that in vibration you have two possibilities, either delta V equal plus minus 1, and this gives you this nice expression for each line of the spectrum, and this could be from any level to the one just after it. The difference between these peaks is 2 omega e xe, or it's the harmonic or harmonics case, which basically is from the fundamental one, the 0, or from the lowest energy level 0, to either 1 or to the 2 or to the 3. And then this is the difference between them. Great. Well, the lowest energy, when we talked about the harmonic oscillator, where we had h nu n plus or v plus half, we said that the lowest energy level corresponding to v equals 0 was half something. Now, if you look into the energy, if we go back here, EV, that's EV. And we divided by HC to get the spectral term GV. Now, if I want to go back to the energy now, what is the lowest energy? Or what is the energy of the lowest level? Well, you put V equals 0. If you put V equals 0, look, it's going to be HC omega E over 2 minus omega E xe over 4. Now, how did it show up? Just because I showed G. So, well, probably I can do that in class when I see you, but it's not complicated. Well, EV is HCGV. That's it. So if you want EV, multiply all this by HC and put V equals 0. And then you will get this. Okay? So, in its lowest energy state, the molecule always possesses small vibrational energy. And this is called the energy of the 0 point. And you usually get asked about this. So what is the energy of the 0 point? Well, that's the energy for V equals 0 in the unharmonic oscillator. Now notice, we define two things. dE is called the energy of the spectroscopic dissociation. And this is basically the difference between absolute 0 energy, which does not exist. So that's why it's a spectroscopic. 0 level, the complete 0, the value 0, and the highest level of the vibrational energy above which the potential goes away, which means that the molecule is dissociated. This is called energy of the spectroscopic dissociation, dE. Now, d0 is just the same, but instead of getting the reference value as the 0 on the spectra, we just get the reference value as E0. So there is a small difference if you want. So dE, if you want, is D0 plus E0. Okay, so if you get dE and you are asked to get, or you seek to get D0, the difference between them is just E0, which is the energy of the 0 point. And D0 is called chemical dissociation because this has a chemical meaning. The molecule is initially at E0, and then when it dissociates, it gets to a level of energy called D0. Okay? Anyway, now we are interested in calculating this D0 or dE, say. How to calculate dE? How to calculate the energy above which the molecule is going to dissociate? Well, as we said, the more the energy level, this is the Morse potential thing, the more the energy level increases, or the more the wave, the vibrational quantum number increases, so we are increasing in energies of the molecule, of the vibrating molecule. And then what happens is, the more the energy gets higher, the more the distance, the separation, the energetic separation between the vibrational energy levels gets smaller. Which means that if V equal 1, well, the vibrational energy increases a lot compared to the energy of the 0 point. If V equal 2, it increases, but not as much. At V equal 3, the third level or the fourth level, the vibration energy gets a bit higher, and then a bit higher. When it becomes really too much energy, it's just a small increase from level to level. Okay, the reason is because we have minus here and we have a square. Okay, so what does that mean? It means that if I'm reaching the level where there is no more molecule after which, it means the difference, so I'm getting the maximum energy of vibration, so the difference between this one and the one just above it is practically zero. Because the difference between levels gets smaller and smaller and smaller and smaller and smaller, and the more I increase until the difference is almost zero or tends to zero, and that will correspond to the V at which the maximum number, basically, above which the energy is broken, that the molecule is broken. So to do that, mathematically, this means that delta G, there's a difference between two levels, spectroscopically speaking, so that's a spectral vibrational spectral term. Delta G, GV plus 1 minus GV, two consecutive levels, they tend to zero or equal to zero. Okay, great. Now, generally speaking, GV, we know it, it's like this. This is the expression of it. We've got that from the very beginning of the Harmonic Oscillator solution. And the GV plus 1, so you just put instead of VV plus 1, so that's the G, the corresponding energy vibration, or the corresponding spectral term for the level just after it, V plus 1. And it's this. And you just calculate the difference between them. And you will get this. It's just mathematics. Delta G for any two consecutive level is going to be omega E minus 2 omega E XE times V minus 2 omega E XE. Great. But that's not all. Now we have to do this. It's called the method of a bridge spooner. Just try to translate this into Arabic. You will find a nice family name. Anyway, so delta G is this expression. We have to know that XE is a very small constant because it's a small correction. And omega E is much bigger than omega E XE because XE is much smaller than 1. So we will first do a first approximation, or bridge spooner, they did a first approximation, where we can basically get rid of 2 omega E XE because it's too small. Then delta G is omega E minus 2 omega E XE times V. Now, as we said, well, to get to know what is the maximum energy above which the molecule is going to dissociate, we have to know what is the V, the quantum number that corresponds to this maximum energy. Well, this must show up from here. Why? Because again, I'm being redundant, but to fix the idea, well, the maximum V will give us the maximum energy, but at the maximum energy, the difference between the consecutive levels becomes almost zero. So this is the difference between consecutive levels. We put it to zero, then this will give us the maximum V, or the V corresponding to the maximum vibrational energy. I'll just put that to zero, and you will see it's omega E over 2 omega E XE. That's the V maximum. The V maximum, if we plug it into G of V maximum, it should give us the spectral term, or the energy of vibration for the highest level above which the molecule dissociates. And this gives us the energy of dissociation, dE. Now, why is it just GV max? Because in fact, GV max, so that's the energy for the Vmax minus zero, minus the absolute zero value to get dE, right? Great. So just put Vmax in the expression of G. So where is G? There's G. And instead of V here, put Vmax. Up, where I'm going. Okay. So if you put Vmax in there, you just do the calculation, you will get to this. Look, it's easy. Omega E over 2 omega E XE, this is V. So V plus half minus, look, omega XE, minus omega XE V plus half. So omega XE V plus half. Okay, but that's still a bit complicated, so we need also to do a bit of calculation. So if you spread it, this will give you, if you develop it, dE equal omega E squared over 4 omega E xe minus omega E xe over 4. It's just, again, mathematics. Okay? Now here, we have to use the fact that omega E xe is much smaller than omega E, so the square is much smaller than the square of omega E. So basically omega E xe, wait a second. Yeah, I mean, I think there's a small fault in here. It's just to say that omega E xe is much smaller than omega E squared. That's all. Because forget the square here. I think it's a typo. It's omega E. I'll put my hand on top of it. It means that omega E xe is much smaller than omega E squared, so that this term here can be neglected compared to omega E squared over omega E xe. And so we end up with dE, and this is the formula of Bridge-Spooner. You might not be necessarily responsible for the demonstration, but maybe. It's not very complicated. But dE, so the dissociation energy, the spectroscopic dissociation energy, is omega E squared over 4 omega E xe. Now obviously you can get from that the D0, as we said. The difference just to add E0. Okay? Now, just experimental values that don't care about. And then finally the Boltzmann distribution, it's the same thing as in the rotation. So we are just looking into the what are the highest possible energy levels that could be occupied by the molecule. Well, we take the lowest energy level, N0, the number of possible states is N0, its energy is E0, so it's EV minus E0 of kBt, and that's the same as before. Well, we don't put a lot of attention into this. In conclusion, well, okay, classical mechanics can do it. Quantum mechanics can do it, but, well, harmonic oscillator is just an approximation, and it's a bad approximation for the real vibration of molecules. We had to introduce a new potential, the Morse potential, which is more real, and actually it shows us that the energy levels of vibration differ in spacing when we get increased, so that we can get actually into the dissociation energy of the molecule on one hand. On the other hand, we can also notice two things. We usually have transitions in absorption specifically obeying the difference delta V equal +1 or -1 for emission, and these have the highest probability. But in the case of vibration, we could have harmonics, which means that we have possible vibration from the level V equals 0 to V equal 2, from V equals 0 to V equals 3, and these transitions are going to be harmonics compared to the fundamental one, which is from V equals 0 to V equal 1. So in this case, we talk about just V equals 0 as the original initial state. Well, I think that all the package now is installed on your systems. The best way to plug and play with the exercises. Thank you for watching, and we will be again